This is problem 109 from chapter 17. The 500 kilogram concrete culvert has a mean radius of 0.5 meters. If the truck has an acceleration of 3 meters per second squared, determine the culvert's angular acceleration. Assume that the culvert does not slip on the truck bed and neglect its thickness. So we have the truck accelerating to the right. And for the free body diagram of the culvert, we have the force of gravity acting downwards. We have the normal force acting upward. Because the truck is accelerating to the right, the force of friction is going to be acting to the right as well. If there was no friction, the culvert would not move with the truck, and relative to the truck, the culvert would be sliding to the left, and friction would oppose that motion, so friction is acting to the right. Or you could say this: when the truck is accelerating, the culvert is going to start rolling backward, which is like this, so the force of friction would be acting so that it would rotate this way. So now that we have our free body diagram, we can apply Newton's second law in the x direction and in the y direction. The culvert is not accelerating in the y direction, so the sum of the forces in the y direction is equal to 0. I have two forces acting in the y direction, so the normal force is equal to the force of gravity. I have the sum of the forces in the x direction is equal to the mass times the acceleration of the mass center in the x direction, but be careful here because this is the acceleration of the culvert, so that's not the same as the acceleration of the truck. And this mass is equal to 500, so we can call that 500 times the acceleration of the mass center in the x direction. Oh, and when I sum up the forces in the x direction, I have one force acting in the x direction, so that is the force of static friction. So let's call this equation 1. Then I get another equation from looking at the sum of the moments, and I can do the sum of the moments about point G, and that's equal to the moment of inertia about g times the angular acceleration. So sum of the moments about g is equal to moment of inertia about g times the angular acceleration. We were told that we could neglect the thickness of the culvert. We can treat the culvert as a hollow cylinder. If you go to the back of the book, it's hollow, so it's not this cylinder. It's like a thin ring, and the height of this ring does not matter. So we saw before that the thin circular disc and the cylinder, if you're looking about the z-axis, the height of the cylinder doesn't matter, and the moment of inertia about this z-axis is the same as it is for the thin circular disc. So for the thin ring, its height here doesn't matter. You would still get about the z-axis going through the mass center, a moment of inertia of mr squared, because all of the mass is a distance r from the z-axis. So this is mr squared times the angular acceleration. And for the sum of the moments, about point G, I'm going to get 0 for the force of gravity. The normal force is when I do the cross product of the vector r, which goes from the mass center to the normal force. That gives me 0. So it's only the force of static friction, which gives me a non-zero moment. That's this distance r, which is the radius of 0.5, crossed with the force of static friction. That would be going this way, is equal to mr squared times alpha. So we said that this was the positive direction, and that's the direction of the angular acceleration. I called r 0.5 here, and I called the r here, but this r is the 0.5 that you have there, so that's 0.5 squared times alpha. So I can cancel this 0.5 with one of those, and that's force of static friction is equal to mass. Let's put the mass in also and say this is 500 times 0.5 times the angular acceleration, so that's 250 times the angular acceleration. And let's call this equation 2. Okay, so now I have two equations here and here. They both have the force of static friction, but the problem is that equation 2 has the angular acceleration and equation 1 has the acceleration of the mass center in the x direction. I need to relate these two. Now, I know that the culvert is rolling without slipping, so I would like to say the acceleration of the mass center in the x direction is equal to the angular acceleration times the radius. However, because the truck is moving, that is not true. So I have the acceleration of the truck, which is going this way, and then I have the angular acceleration of the culvert. So if the truck was not moving, I could just say this is equal to the radius times the angular acceleration, but I have to take into account the fact that the truck is accelerating. So that means I get to go back to equation 1618, and I'm going to look at the culvert. And I'm going to pick the point which is in contact with the truck at this moment. I'm going to call that point A. And I have here the acceleration of the mass center, so that's point G. And I'm going to use equation 1618 to find the acceleration of point G. So the acceleration of G is equal to the acceleration of point A plus the angular acceleration of the culvert crossed with the vector r, which goes 2g from A, minus the angular acceleration, the angular velocity squared, times my vector r, which goes to point G from point A. So point A is a point on the culvert. Because the culvert is rotating, we have a normal component, and we also have a tangential component for the acceleration of point A. If I look at the acceleration of point G, we said that the acceleration in the y direction is equal to 0, so this is just the x component. And my acceleration for point A is going to have a normal component and a tangential component. The tangential component is pointing this way, the normal component is pointing this way, but since I used x and y components up here, I want to say the tangential component that's going in the x direction, so I have a tangential component for point A. Tangential component for point A going in the I hat direction. And then I have a normal component going in the j hat direction, plus the angular acceleration, which is the same as the angular acceleration that I have here, and that's crossed with a vector which goes to point G from point A. So that's my vector that goes to point G from point A. The angular acceleration is like this, so that vector is pointing out of the page, and when I cross that with r, I get something going to the left, so that's in the negative I hat direction, and the magnitude is alpha, and this vector r has a magnitude of 0.5. And that was to the left. Okay, so I got the negative sign there, and it's I hat. Then I have minus omega squared, and this vector here that's going in the j hat direction, it has a magnitude of 0.5, so that's 0.5 in the j hat direction. Now thankfully, because we're looking for a relationship between the x component of the acceleration of the mass center and the angular acceleration, we just have to look at the I hat components. So we can say for the I hat components, I have the x component of the acceleration of the mass center, and that's equal to the tangential component of the acceleration that's pointing to the left for point A minus the angular acceleration times 0.5. So now I just have to figure out what this is. Well, we are told that the culvert is rolling without slipping, so that means this point A at this instant in time is not moving relative to the truck, so the acceleration of point A in the tangential direction must be the acceleration of the truck. So let's say the tangential component of the acceleration of point A is the acceleration of the truck. So that would be 3 meters per second, and that's going in the positive x direction. So this is 3 minus the angular acceleration times 0.5. And I was asked to find the angular acceleration, so I want to go back to equation 1 and put this in for the x component of the acceleration of the mass center in equation 1, and then I can set equation 1 equal to equation 2, and then I'll have my answer. So now using equation 1 and equation 2, I have from equation 1 500 times 3 minus the angular acceleration times 0.5 is equal to equation 2, which is 250 times the angular acceleration. And the mass was 500. The mass is the 500 that I have here, and in this equation here it was the mass times 0.5, so the mass cancels out, so the mass of the culvert does not matter. So if I cancel out the mass on this side and this side, it would be this would become 0.5 again. And then I can solve for the angular acceleration. So I bring this over to the other side, and I have 3 is equal to the angular acceleration. Well, that would be putting my units back in, 3 radians per second squared. And we said the angular acceleration was going in this direction. That was the positive direction, and since the angular acceleration turned out to be positive, it truly is going in that direction. That concludes problem 109.